Okay, welcome back. I hope we had a great spring break and are energized, ready to go for the rest of the term. We'll take our quick look at the calendar. Today is class number 18. There are a total of 42 classes during the semester, but we lost 2 snow days, so we're at 18 out of 40, which is just about halfway for the semester. So we're right before the midterm at the moment. Again, lots of stuff is due today. Project number 4, the Gamma project, throw it in the folder if you have it. Project 5 is now assigned. It has to do with these chocolates. So again, make sure you leave here with 4 different kinds of chocolates. This project is due 1 week from today, Monday, March the 30th. And the other thing that was due today was the take-home quiz about the U substitutions. So throw that in the folders as well. All right. So in terms of the test corrections, I'd love for you to check my arithmetic later just to make sure that I gave you back the points that you were supposed to get back. Like I gave you back every part of the points on question 1B, but then a third of the rest of the points, and I just did that all on my own. So I'd be surprised if I did it 100% perfect. So just check the arithmetic and let me know if I made any mistakes. What I didn't do was update your current grade on that page. All I did was change the test grade. So if you want an update based on your new grade, just see me right after class and I'll provide it. And the other thing about this chocolate project is that the directions on number 4, can everybody just take a look at I guess it's probably the back of the last page on the chocolate one. So the directions on number 4 say that they're a little bit different than the directions on the first 3. The first 3 are all the same. So the 4th chocolate in this case is the egg, right? So when I did this project a couple years ago, the egg that I could find was flat on one side. It wasn't like egg-shaped like the one that I have today. And so when it was flat, we needed different directions, but the ones that I got over break were not flat. So the directions there are actually supposed to be exactly the same. So cross them off. You're going to ignore the directions on 4 and just do the same directions you've been doing all the way up until that point, okay? So cross off the directions on 4, just follow the directions from the rest of the project. Okay, so I think we're ready to jump in on the top of page 38. Today we continue our work with volumes. We have one more day next class on volumes and arc length, and then we start doing some more applications of the integral, including some physics and economics and probability. So that's what's coming. And then, yeah, so let's jump in. Okay, so our summary, let's go to Cooper. Thank you, Steve. Okay, so take a look first at the rectangle. We're going to spin that rectangle 360 degrees around this horizontal line. That's the axis of revolution. And we're going to create a 3-dimensional solid. What is the name of that solid? That's a cylinder. Everybody see it? So we're going to push ourselves to think 3-dimensionally here. Every time we're going to take the shaded region and spin it around the horizontal line. How do you have so many of these? Yeah, one of each. You're taking Sam's candy for it. Okay, how about the semicircle? What happens when you rotate it around? That's a sphere. And how about this triangle? It's a cone, right? It's not a pyramid. This is a cone. It's round as we go around and round. So that's our cone. And then finally, the last guy, I don't really have as nice a name for it, but can you picture it? Yeah, like a pipe is good. A pipe with some thickness to it, right? So we'll say a thick pipe. I think I heard somebody say PVC tubing. That's good too. Okay, and so we'll just draw the picture on this last guy maybe. So as we take this point and swing it all the way around the axis, we get this circle here, right? And then I'll take this top point here and I'll swing it all the way around and I get this other circle. And then the same kind of thing happens on this side and then we connect. And so there's our pipe with some thickness. And we'll go to number 2, Gabe. Okay, so let's do a slice right here. So our slice is going to be like our little rectangle, and it's going to spin around. So if I take that thing and I spin it around my axis of revolution, what kind of a shape do I get? Circle is good. We're going to call that a disk. I always forget. C or K? C. C. Right. So yes, it's a circle. It's got a little bit of a thickness. We're going to call it a disk. What about taking the same kind of rectangle shape over here and spinning it around? That's another disk, right? It doesn't matter what it comes from. How about in the triangle here? That's going to be another disk. Yeah, but this last guy is not a disk, right? If I take this rectangle here and I spin it around, yeah, we're going to, it's a disk minus another disk, right? And we're going to call it a washer. I'm speaking to the, yeah. It's not a torus. Yeah, torus is a donut, but yeah, we'll call it a washer. All right, yeah, and you guys imagine, right, like the metal washers, that's what they look like. Again, a little bit of thickness. Okay, so then the fact is, it doesn't matter what the original shapes look like. If you spin a slice, a rectangle, around an axis, you're going to get either a disk, a disk, a disk, or a washer, right? It doesn't matter how crazy the generating space was. Okay, so here's a crazier looking picture in number 3. Here's our funny region shaded in, and we take same kind of rectangular slice here, and we spin it around, and what kind of a shape do we get? We get a disk. It doesn't matter that it's kind of this weird curve that's that it's coming from, and so if you take that green thing and you spin it around, you get that blue disk right there, and we get this kind of like bell-shaped three-dimensional solid. Super. And then the same kind of thing, even if you have two curves, here there's a y equals f of x on top and a y equals, I can't read it, is that a g? An r, g of x on the bottom. And again, you take your disk right here, and we spin it around. Lo and behold, we just get another washer. And the washer is going to change outer radius and it's going to change inner radius, but it's just a bunch of washers that get put together and make this kind of like bell with a hollow inside. Okay, so on the next page, we'll go to number 4, Petru. Thank you. So we're going to take a quick look at a sketchpad thing. I did not make this, but here is the idea for a disk or a washer. We're just going to revolve this guy going back behind the board and then coming out in front of the board. And is that a disk or a washer? Disk. And so if we were to, I think it's this point right here. Is that right? No, I think it's the other guy. Sorry, maybe it is this guy. Okay, so then if we now just look at this blue thing is going to be the part that's shaded in, what kind of a shape are we going to get? It's a washer, right? Okay, so that's the basic idea with a disk and a washer. That's one of them. Now we're going to take a look, yeah, we'll see shells later, but now we're going to take a look at this region right here that's kind of highlighted in red. Imagine spinning it around the x-axis, the axis of revolution here, and we'll get this kind of like bowl shape, right? Pretty small at the left and bigger at the right. And so we can revolve one rectangle, and that's fine, or we can see a whole bunch of rectangles. Now that is not exactly the shape, right? That's like a wedding cake type thing, but this is using only 5 disks, which would be a pretty rough approximation for the shape itself. But how could we get a better approximation for that solid? There's more. Yeah, and so infinity, or how about just 10? But, all right, so there are 10, and it looks closer to the actual solid that we would get, right? And the more disks you use, the better you get in terms of heading to that real volume. And we'll go to infinity, which will lead to an integral to actually find the exact volume of that thing. Last one is this. If I take this slice and I revolve it around the axis of revolution, is that a disk or a washer? It's a washer, right? Because we got that space in between. And so you can imagine maybe taking that blue highlighted area and spinning it around the axis of revolution. So coming out of the board and then going back behind the board, and we get that three-dimensional solid there, right? And we can just imagine that 3D solid is being created by a bunch of these washers of various dimensions. All right, so that is what we're after. And the goal today is to find the volumes of all of these solids of revolution. And I will remind you, this is a few pages before, you don't need to go back and find it, but this was something we saw in our very last class way back on Friday. And it said that if you happen to have a formula called A of X for the area of a cross section, just like up here, we had this, like, remember the really weird looking shape with all the square cross sections? And it turned out all we needed was a formula for the area of that cross section. We found its volume actually with a little dx at the end. If you just integrate the area formula, you will find the volume. So this is what we're going to be doing today. So let's, we're only going to do single integrals this semester, but next semester you'll get to do multiple integrals. Yeah. Okay, so let's try number 5 here. So it says find the volume of the solid that's obtained when the region bounded by y equals square root of x, x equals 1, x equals 4, and the x-axis is revolved around the x-axis. Okay, so the first thing we need in order to make some headway here, we're going to see a formula in just a minute, but you got to have a picture. Like, forget memorizing a formula. We need to know what this looks like. So y equals square root of x, can we imagine, right? It's just a parabola, but opening which way? Square root of x opens which way? To the right, yep, and it's only the top half, so there's y equals square root of x. Now at the moment, I have no earthly idea where the region is. It doesn't exist until it's bounded on all sides. So it could be below the curve, it could be above the curve, who knows? So we keep reading, x equals 1. What kind of a line is that? Is it 45, is it horizontal, x equals 1. Vertical, right? So x equals 1, we'll draw that guy. Here, x equals 1. I still don't have a region enclosed, and don't read too much into the axes. They're not part of the region until it says they're part of the region. X equals 4, okay, great, that's over here. All right, we're getting close. We still don't have a region completely filled in yet. And then what's the last line in this region? Before we revolve it, but what's the last defining boundary? Is the x-axis itself. And so now between all 4 of those things is a well-defined enclosed space. Can we see it? I'll shade it in and then it'll disappear. It's here. That's the space that we're talking about. Yeah, so we're never going to run into something where, so the axis that we spin around will never be part of the region that we're rotating. Yeah, good question. Okay, everybody sees the region? Steve? I think that suppose that I had decided that my region was going to be there, right? I could cut it off before we get to the x-axis. So just, yes, it would have to be noted. But I think we need the x-axis to formally make a boundary. And just as well, I could take this space that we're talking about here and I could spin it around the y-axis, right? I would get this really kind of weird looking shape. But the axes are not necessarily, the thing you spin around could have absolutely nothing to do with the region itself. So we've got to have a perfectly well-defined enclosed region, and then separate from that, independent from that, okay, tell me what we're spinning around. Good questions. Okay, so we're going to find the volume. We're going to spin this guy around the x-axis. So we'll put that here in red. Just put a little indicator. That's what we're spinning around. And so you're welcome to draw, like I'm going to draw the rest of this. You don't need to draw this at all, but I could imagine drawing like the mirror image down here and spinning this guy around here and here. Can we kind of see like the bowl, but it's really flat on the bottom? You don't need to draw the 3D part. You just need to have a good 2D vision of this thing. And so according to what we flashed up on the screen a minute ago, if we could just find a formula for the area of a general cross section. So let's pick a generic point How about we call this point right here x comma y? And I'm looking for the area of a cross section that hits there. So would you say that is a disk or a washer? It's a disk, right? Because one of the boundaries is the x-axis itself. It's a circle with radius y. It's true, isn't it? Here we go. A of x equals. That is a circle. The area formula for a circle is pi r squared. Would you say that the radius is x or y for that circle? It's y. Okay, so pi times y squared is exactly the area, and it changes, right? As y moves, that area changes. Yeah, and the 3D part is going to be the dx, which came from a delta x, a little bit of thickness. Yeah, right. Yeah, we need to get it in terms of x. So we've written it the easy way. It is pi times y squared, but this is going to be an x integral because this is an x cross-section. Cross-section's perpendicular to the x-axis. Super. So pi times, and then instead of y squared, we gotta put, yeah, what is y equal to according to that blue curve? It's the square root of x. So this one doesn't involve a whole lot of work translating, right? You just change the y into a square root of x. And that simplifies to pi x. And I just want to, again, make sure we're clear, like that pi x is just the area of a particular cross-section. If you plug in x equals 2, it looks like my cross-section here roughly in the middle is maybe around x equals 2. What's the area of that circle? Oh, it's exactly 2 times pi. What's the area of the biggest circle here? 4 times pi. It's not news, right? But let's see, if x equals 4, how much is the height? It's 2. And so when I do pi times 2 squared, I get 4 pi. It's just generalizing, like it's not a specific cross-section, it's just the general one. And so according to what we saw, this thing here in black at the top, all I have to do is stick this cross-section area formula into an integral and let the integral work its magic, and that will be my volume. So let's finish this one off here. So volume equals integral from where to where? 1 to 4, right? X at the left, x at the right is 1 and 4. My a of x function is pi times x. And then the dx, as Rob pointed out, that's actually representing a little bit of thickness that we're giving these circles to make them 3D disks. But it's just a symbol there. So for us to be able to do this process, they have to be perpendicular. We have to have but they don't have to be perpendicular, but you have to draw your cross sections perpendicular to the x-axis. So you won't see anything going. Yeah, I think we're okay. Let's see. Yeah. Yeah, so whatever that number is and whatever that number is, no problem that these are just points. They're just the far left and the far right, and I can still imagine a perfectly up and down rectangle in the middle of this thing. So then I think that would get embedded in the area function. I think that the 45-degree line, the boundaries of this guy, helps you figure out what the area function is, but it's just got to be two numbers a number at the left and a number at the right for the limits. Good question. Okay, so let's just get an answer here because we're so close to the end here. What do we get? Pi times x squared over 2 from 1 to 4. So what is that? 16 pi over 2 minus pi over 2. 15 pi over 2. So we're going to rotate only around horizontal or vertical things. And we're going to do, yeah, it's going to be moved, and we'll do it on the next page. Okay, so I said there was a formula. I'm not a fan of just memorizing this formula. Everybody have what they need on this one? So the formula down here at the bottom says pi times f of x squared. That is not a formula that I have memorized. But if we actually, and we didn't use it in the example that we did up above, but apparently pi times, what was the function in this case? Square root of x. And do you see that's what we ended up with pi x, and of course it comes from that guy right there, but I really just think pi times r squared, and then I figure out what the r is. Oftentimes it's just the formula, the function. Okay, and just highlighting at this stage that the slice, whenever we do disks, is always perpendicular to the axis. So if we were spinning that same region around the y-axis, we would have to draw a horizontal slice. But just a note. Okay, on the next page, one more example. And I think this is what Elia was after. We're revolving now around the line y equals -2. Same region, same quick sketch. So we've got square root of x equals 1 and 4. And then the x-axis, same region. But now we're spinning around the line y equals -2. What kind of a line is that? That's a horizontal line. Right, so I'm going to draw my horizontal line right down here. That is my y equals -2, yeah? And so if we spin that region around that line, we're going to have some space in the middle of this solid, right? Solid that you can kind of see right through the middle of. Yeah, and basically the disk minus the inner disk is what we're calling a washer. And so we take this guy, we spin it around. I won't draw the whole 3D thing, but I will just draw my representative slice. So here's my rectangle somewhere in the middle. Again, calling this a generic XY. I think that's an important step, just naming it even though it's generic. And we take that thing and we spin it around and we get this washer going out of the board and back behind the board. And I'll come back to my basic formula that we saw before. If we can somehow get our hands on an area function, we just throw it inside of an integral and we'll have our volume. So we got to come up with an area formula here. Let's try it. A of x equals. What is it? Yeah, we're gonna have some kind of a difference in here, right? Because there's a space in the middle. Yeah, how much is the big radius of this washer? It's y plus 2, isn't it? Because it's 2 bigger. We need to see the radius of the washer drawn, right? The radius used to be just y, but now I've gotten the radius to be 2 units bigger. So it's a y plus 2. All right, I can do that. So that's pi times y plus 2 squared, right? Pi r squared minus pi times 2 squared. Right? Isn't that the area of the washer? The washer is just the big circle minus the little circle. So those are my two areas, and we subtract them. Okay, and then just like before, we need to make it so it's x's only. So this becomes pi times yeah, and so the y becomes how much for that curve? Square root of x. So that's the formula we're going to stick inside of our integral. Okay, so we'll just write the formula and then we'll call it done. Integral from where to where? 1 to 4. And then that entire area cross-section formula just goes right into our integral. So this integral isn't hard to do, but it's not worth our time at this moment. Any questions on setting up this problem? Yeah, you'd multiply everything out, and then you'd have term by term things you could integrate. Yeah. Okay, so that would be the, whatever you get when you crunch through, that would be the volume of this sort of crazy shape there. And so here's another formula. Again, I don't encourage you to memorize it, but it's pi times the outer radius squared minus pi times the inner radius squared. And you just got to make sure you, because yeah, it's just the area of a circle, so don't memorize it. Right. Yeah. Okay, so there is a, have you guys ever heard of a lathe? I think I'm saying that right. Lathe, how do I say it? Lathe. Yeah. Yeah, so like you take a piece of wood or something, you have it spin around really fast, and then you carve into it and make these really nice shapes. So every one of these really nice shapes you make with that machine is one of these solids of revolution, right? Because it's just spinning around, and all you're doing is changing the outer function. And so there's this website you can play around with. So I'm just going to draw some stuff here, and it's going to create over here the 3D revolved version. So if I take that guy and then I connect lower, or I can maybe come into itself, right? I don't know if a lathe can do that, but yeah, you can go into itself. I guess there's a limit to how far. Yeah. So anyway, so you can play around with that, but in theory, if we can just like we can just throw this thing, if we had a formula for the outer defining edge, we could just throw it into our formula, into our integral, and have the volume of this really crazy looking thing. Okay, so the activity is on the next page. Again, take your time drawing the regions. Yeah, Levi.